Thank you, Leandro. So I will be talking a little bit about improving current Stark provers and some of the strategies we have, since, well, we are here to discuss SQL acceleration, and that can help us a lot. Of course, as we will see, that will depend in the use case we have and in identifying correctly the bottlenecks we have in Stark provers. So this is an outline of my talk. First, I will be giving a brief introduction to Starks in case you don't know, so that you know exactly which parts compose the protocol, and then we can discuss how to improve them. Then a little bit about Stark Platinum, which is our prover. In the previous talk, Francisco mentioned he's using it, so we are super happy it's gaining acceptance in the community. Then we will discuss some areas where we can improve performance regarding field arithmetic, hash functions, proof size, and lookup arguments, and then finish with some conclusions. Okay, so what Starks? Starks are simply scalable, transparent arguments of knowledge. This means that these arguments of knowledge do not need a trusted setup and are conjectured to be post-quantum secure, and that the proof can be verified much faster than naive re-execution. So what are the ingredients or the steps for Starks? First, what we need is an execution trace of the program, which is a table containing the evolution of the registers at each clock cycle when we execute the program. Then, for those transitions to be valid, we have a set of polynomial constraints that are defined over the trace, and these are called the algebraic intermediate representation of the program. Then what we have to do is show that the trace satisfies these constraints, and to do so, what we are going to do to be able to prove it in a succinct way is interpolate the trace. So what we are doing is encoding each column of the trace as a univariate polynomial. And to do that, we have to do it efficiently. We are going to use the FFT. Of course, that forces us to use what we call FFT-friendly fields, which are fields containing a large subgroup whose order is a power of 2, a large power of 2. Okay? Then, to commit to those polynomials, we'll have to build Merkle trees from the evaluations of that polynomial over a larger domain. And again, there we will use, to build the evaluations, the FFT, and then Merkle trees, for which we need hash functions. And once we have these polynomials, in order to prove that the constraints are satisfied, what we need to do is, first, compose the trace polynomials with the constraints, so as to enforce the constraints over the trace, and then divide the constraints by the vanishing polynomial over which those constraints are satisfied. And once we have that, in Starks, what we have to prove is that that quotient is in fact a polynomial. And to do that, we are going to use Fry, which is simply a fast-read Solomon interactive oracle proof of proximity. Okay? So Stark Platinum is our implementation of a general Stark prover. You can see the repo over there and follow all the developments in LambdaWorks in our channel. It's written in Rust with focus on security and performance. You can use it to prove code written in Cairo. There is a special folder which contains the Cairo error, but you can then also use it to generate your own error, and we are currently trying to build a drop-in replacement for Winterfell. And we are working towards full compatibility with Starkware Stone Prover, so that then you can verify your proofs with the L1 verifier. So we saw that one of the things we have to do is FFTs, quotienting, and all that. All that is related to field arithmetic. So the original Stark prover works over a 252-bit field, and the best arithmetic we have is Montgomery arithmetic. And, well, we are constrained to use FFT-friendly fields to compute efficiently. So of course, this does not give us enough freedom to choose maybe other types of fields. But right now, the idea is using smaller fields such as mini Goldilocks or Mersenne primes, which have special reduction formulae. And that way, we can compute everything faster and also use less memory, especially when we try to represent things in the VM with a field element. Here we can use, if we use mini Goldilocks, we can use 64-bit registers. Of course, one drawback of using smaller fields is that then to get to the desired security, we have to extend it, and so we have to work with extension fields, which adds a little bit more complexity, but nothing else, okay? And to use these smaller fields, of course, we have to make some small changes to the VM. As regards to hashing, especially when we want to do recursion, we have to prove a lot of hashes. So one thing we would like is to use arithmetization-friendly hashes such as Poseidon or TIP5, but the problem is that these hashes are much slower than traditional hashes such as SHA-3 or Blake. Of course, maybe with some help from hardware acceleration or specialized instructions, we can get much better with these hashes that especially contribute to a significant overhead in the Frey protocol. Of course, what we can do in the Frey protocol to avoid all these commitments is try to skip layers, which means committing to every second or third layer, for example, reducing the amount of hashes the prover has to do. Finally, regarding proof size, well, there are some optimizations that avoid sending elements that can be directly computed by the verifier from information the prover has already to send. Another thing we saw is that in the case of the Stone prover, we have to send 2 evaluations per query from every layer. And if we group both evaluations in the same branch, then we reduce the amount of authentication paths that we have to send. Of course, another advantage is using page inclusion proofs, which reduces also the number of hashes that have to be calculated. And of course, in the case of the Frey protocol, it can be interesting to skip layers. And originally in Frey, one had to wait until one reached degree 0. Of course, we can make some optimization by finishing before it reaches degree 0. So those are some of the tricks you can use to reduce proof size. Another one has to do with, of course, the serialization format, and we are working towards that. And well, another important thing is when one tries to prove things with the VM, there are some operations that cannot be expressed efficiently as VM instructions, and so maybe we need like a specialized coprocessors, for example, having, in the case of StarkNet, you have built-ins for the operations of elliptic curves and signatures and hashes. So, of course, right now, the problem with these built-ins is that we have static layouts, meaning that we have just one layout, and meaning, for example, we have this box, and if we want to send something this small or something this large, we are paying always the same cost. So maybe by switching to dynamic layouts, we can get much better for users not wanting to do specifically blockchain operations or blockchain-related applications. And also we could use maybe something like chiplets, for example. That is something that the Maiden VM has. Of course, one of the main costs here when we want to check either the built-ins or the memory consistency is related to the grand product check. So we have to do a lot of sorting of large vectors, maybe computing some inverses. So in general, this is like quite expensive. We can get, of course, much better by using new techniques. For example, the logarithmic derivative lookup offers some advantages for some commonly used operations. For example, one operation one has to do a lot of time is rain check. And in the case of the Maiden VM, when they switched to the logarithmic derivative, they reduce the amount of columns the prover has to commit to, and that reduces also the calculation time. And right now, or a few months ago, we had like an improvement with lookup by adding the GKR protocol to prove the lookup. So we expect that this will mean a significant boost to the provers. And well, finally, a word on security. The security in the case of Starks depends on 4 parameters. The first one is the field size. So as long as the field is much larger than the evaluation domain, we are on the safe side. Of course, if we use smaller fields, we are forced to work in general with degree 3 extension fields. Another thing is the hash function, but in general, what we have to do is just use the correct digest size. If quantum computers were to appear, then we would have to increase the digest size to the double, and that would double the proof size, but that is something that at least we can live with. And then there are like 2 things that determine the final security. One is proof of work, which just increases the cost for the prover to generate favorable queries, and the other has to do with the number of queries. So each query more or less achieves bits of security. But, well, that depends also on the margin and the assumptions you want to take. If you want to use provable security, then you need to do lots of queries, but you are always on the safe side. But most of the projects have been working with conjectural security because we still don't have like a better bound. And so far, they've been working really, really well. Okay. So thank you very much for your attention, and if you have any questions, happy to answer.
Thank you, great presentation. I wanted to quickly ask about the benefits of using chiplets versus built-ins.
Well, the problem right now with built-ins, as you have them in StarkNet, is that you have like fixed layouts. They were optimized for the operations StarkNet has to do. But really, if you want to do something else, maybe those layouts make you pay a significant overhead. With chiplets, you have a different ordering. And if you see, for example, in the case of the Maidan VM, first they put all the information from the hash chiplet, then the elliptic curve, and so maybe that gives you like a nicer trace to prove. But we hope that we can, after we achieve compatibility with the StarkNet prover, we can then move on to implement some other layouts so that you get specialized provers to prove your application and not just StarkNets.
Thanks.
Hi, Christian here from Dateo. You mentioned on your hashing slide things like Poseidon being arithmetization friendly, good for recursion, but much slower than SHA-3, for example. Now there's a new hash function just a few months old called Monolith that gets the best of both, right? Similarly nice as Poseidon, but the same speed as SHA-3. Isn't this a bit of a game changer for you also?
Yeah. In fact, we are implementing it in LambdaWorks. One of our interns said, I want to add that, so now we are going to try and play a little bit with it. Luckily, we get the best of both worlds.
Great to hear, thanks.
Well then, thank you very much.